In this section, we'll consolidate what we have learned in the previous subsections. Given some examples on recursive relations, we'll use iteration to guess the explicit formula. Then from there, use mathematical induction to verify the correctness of the explicit formula. In this example, a sub 0, a sub 1, a sub 2, etc. is a sequence defined recursively by a sub n is equal to n times of a sub n minus 1 for n greater than or equal to 1, with the initial condition a sub 0 equal to 1. We are to find the explicit formula and to use mathematical induction to verify the correctness of the explicit formula. Let's start with part 1. To use iteration to guess an explicit formula for the sequence, let's do step 1. Start from the initial conditions. It is given as a0 equal 1, so copy that down. Next, step 2. Calculate successive terms until you see a pattern developing. To calculate the successive terms, use the recurrence relation given above. So a1 would be equal to 1 times a0. But a0 can be substituted with the previous term, which is equal to 1. So a1 is equal to 1 times 1, which is equal to 1. Similarly, a2 would be equal to 2 times a sub 1. But a sub 1 can be substituted with the previous term. So a sub 2 is equal to 2 times 1, which equals 2. Next, a sub 3 would be equal to 3 times a sub 2. But a sub 2 can be substituted with the previous term. So a sub 3 is equal to 3 times 2 times 1, which equals 6. Next, a sub 4 would be equal to 4 times a sub 3. But a sub 3 can be substituted with the previous term. So a sub 4 is equal to 4 times 3 times 2 times 1, which equals 24. Next, a sub 5 would be equal to 5 times a sub 4. But a sub 4 can be substituted with the previous term. So a sub 5 is equal to 5 times 4 times 3 times 2 times 1, which equals 120. Are you able to see any pattern yet? Well, if you focus on these two areas, you will notice that 1 times 2 times 3 times up to the subscript number. Hence, in step 3, to guess the explicit formula, we can infer that for any generic n, a sub n is equal to 1 times 2 times 3 times all the way to n, which can be written in shorthand as n factorial. Now that we have found the explicit formula to be a sub n is equal to n factorial, how can we use mathematical induction to verify the correctness of this explicit formula? Well, the question has given us two vital pieces of info. First, the initial condition a0 is equal to 1. Second, for any integer n greater than or equal to 1, a sub n is equal to n times a sub n minus 1. These info are a given, so we can make use of them later. To do the actual proof, we begin by writing down this framework first, then filling them up one by one. First, we state the property to be proven, P of n, which is a sub n equal to n factorial. Next, we prove the basis step for the smallest n, which is equal to 0. According to the initial condition, In this case, we replace all the n's in the property to be 0, and we will get p of 0 as a naught equal to 0 factorial. To prove that, we show that the left-hand side, which is equal to a naught, is actually given to be 1, while the right-hand side, which is equal to 0 factorial, evaluates to 1 as well. Since left-hand side is equal to right-hand side, the property is true for n equal to 0. Next, we are going to assume that the property is true for n equal to k. Replace all the n's with k's, and we get p of k to be a sub k equal to k factorial. And we assume that to be true. Next, prove p of k plus 1. Replace all the n's with k plus 1, and we get p of k plus 1 to be a sub k plus 1 equal to k plus 1 factorial. And that is what we are going to prove. To do that, we start with the left-hand side, which is equal to a sub k plus 1. How do we get that? Well, we are given this recursive formula. And since n is any integer greater than or equal to 1, we can replace n to be a generic k plus 1. This subscript k plus 1 minus 1 can then be simplified to get k. So a sub k plus 1 is equal to k plus 1 times a sub k, which can then be substituted here. Now, since we have assumed that a sub k is equal to k factorial from p of k above, we can replace a sub k and end up with bracket k plus 1 times k factorial. But k factorial can be expanded, and the whole expression should equal k plus 1 whole thing factorial, which in turn is equal to the right-hand side of the property. Hence, we have proven that p of k plus 1 is true. Finally, we state the conclusion by saying that since we have proved the basis and the inductive steps, the property p of n is true for all n.